So thank you for coming. My name is Barry Genova. I'm the platform technical lead at Bungie. I'm going to talk about multi-threading the Destiny engine. To start off, this talk is not about multi-threaded primitives. We're not going to be talking about atomics. We're not going to be talking about semaphores. It's more about the engine structure and strategies to increase parallelization in the engine. And we're also going to describe our system to help program in multi-threaded ways to prove that it's safe. So sections, brief overview, and then I'm going to talk a little bit about multi-threading. I'm going to follow that up with how we did multi-threading in Destiny, what our philosophies are, and then how we ended up mapping that to the hardware for the different platforms that we shipped. I'm going to talk a little bit about how we proved that our code base was thread safe, and then how we deployed that into our engine, and then the lessons learned from that. And finally, I'll just wrap that up. So Destiny is a shared world shooter. We want to provide low latency action. It's a fast-paced game. It's basically the start of a new generation for us. We're sunsetting Halo. We're starting with two new consoles, the PS4 and Xbox One. And then, of course, we're still shipping on 360 and PS3. A little bit of gameplay footage in case you're one of the people who aren't the 16 million people who've played our game yet. So I'm going to talk a bit about multi-threading, why we needed to do it, how we knew it was going to be hard. Basically, we determined that we couldn't ship without multi-threading. The gameplay needs to be the same across all of our platforms. We want everybody to have the same experience regardless where they're playing it, if they're playing it on last gen or current gen. But we've already shipped on last gen. This workload is now much more than we've done in the past because we're doing both AI and networking in the same game modes instead of just networking for PvP and PvE being single player. Our PvE is now shared. And so we have to basically be able to extract as much CPU as we can out of the whole system, especially on those last gen platforms like PS3 with the two PPUs that aren't very powerful. But we knew multi-threading was going to be hard. So we had to figure out a good way to do it. There's basically three big hard things in it. Splitting the workloads. You never really know what the right way is to split things. Preventing the data dependency misses. Knowing how your data is going to interact with each other. And then tracking down those issues when you've missed all of that and figuring it out. So as an example for splitting the workload, I'll take a look at our object move. Basically, object move, calculating the positions and the skeleton positions by combining, physics update, animation, IK, etc. And so this is usually difficult to parallelize code. It tends to be very branchy. You want it to be branchy because you want to be able to improve the responsiveness. But you have that trade-off. Maybe you don't want to do that. Maybe you want to make it so it's easier to thread by making everything the same and getting rid of those branches. But at the end of the day, each object is going to want to do something different. The objects are interacting with the other objects in the system. How do you deal with that across the threads? And then as they're moving through the system, the things that they're interacting with are changing all the time. It's just a difficult problem to actually figure out the right way to split. And then you're missing data dependencies. So let's say you have some workloads that you've got here, like your AI update, which triggers raycasts and triggers the physics update. Physics update's going to then trigger the audio update because maybe you've got obstruction or occluders that needs to be aware of what's going on in the physics world. And so you can see this part here with the physics box that's moving back and forth. I mean, that job can start late. It can run long. You don't really know what it's going to actually overlap with, especially if you're just dependency bound here. And so there's this missing data dependency on the raycasts reading your physics world versus the physics world actually being updated. And then the rare bugs. You know, you get a bug from QA, they send you a video, that's all you got. It's not a crash, you don't have a core dump, you can't inspect anything. You just get this video that says, hey, the rocket effect on this player is the wrong one. It's the same as this other player. What's going on here? And that's another bug that's just, how are you ever going to debug that? You know, you don't know if it's ever being reproduced in-house. You don't know how many times it's actually gone on. And then QA can't really tell you anything. Maybe they told you, hey, a join in progress happened. So I'm going to talk a little bit about the multi-threading that we built for Destiny principles. First and foremost, we wanted to keep it simple. We wanted our complexity to be necessary. And there's definitely complexity that we have, but anything that we could keep simple definitely helped us out. And we wanted to keep everything as cross-platform as possible. With the 4 platforms that we're shipping on, it's a nightmare to have to keep separate implementations and keep maintenance on those. It just doesn't make sense. And then the biggest important thing was having to understand our data access patterns. If you don't know what your data is doing, it's just going to be really difficult to multi-thread. We also didn't want to wait for synchronization. Synchronization just takes time. We don't necessarily have the CPU time to actually do that. Basically, we shied away from using synchronization primitives wherever we could. We just wanted to express everything via dependencies. So work that could start would start. And if it wasn't ready to start yet, we would just start some other piece of work. Like many other engines, it's basically the flow of the system is running from simulation to rendering. You want your game world to be simulated. You want to put it on screen. We pipeline that, so our rendering is overlapping our simulation. You'll have the previous frames rendering, finishing off while your next frame simulation is going, vice versa. We use a job system. They're pretty well described by now. Definitely seen lots of talks on them. Ron's talk from GDC 2010, definitely a good one. The job, if you're unfamiliar, it's just a self-contained task. It's got some parameters, tells you what to do. For our system, we have them at half a millisecond to 2 milliseconds. And that reflects that our jobs do not get preempted and that we have a significantly high overhead on the jobs. It's not like making a bunch of SPU jobs where you have that sea of jobs because you can run 2 microsecond jobs and not really worry about it. It's priority-based, first in, first out, nothing really fancy there. Our job graph, again, takes into account all the different types of cores that we have. So on PS3, that's going to be both the CPU and the SPU jobs. And we use dependencies between our jobs. We don't do fences. So in this example, we have our AI kickoff and AI finish bookends that have the dependencies for those actor update jobs that would be running in parallel there. What we did find, though, is most systems tend to do the same work every frame. You're just going to run that code over and over again, and it's basically pretty linear. Kind of reflective from olden days where you're using a single thread to do that work. And then most of that work is using the same data, and that data access pattern is going to be the same across frames. So we formalize this into a first-class citizen, which we call the fiber system. So we took this industry standard word fiber and totally corrupted it. I'm sorry. For us, a fiber means a set of jobs that are going to run in sequence. They will not run in parallel with each other. They can run with other fibers, but these ones will always run. And we'll call that sequence of jobs. So in this case, network update, network send, network receive. Those would be 3 jobs that form an iteration for our fibers. And then the other piece that goes with our fiber system is there's a set of data that's associated with it. So in this case, the network state that's accessible by all of the network jobs inside that fiber. For Destiny, we have 3 to 4 fibers, basically. Our simulation contains all the game logic, as you would expect. Similarly, the networking is all of the networking code. And then we have a couple of fibers for rendering that covers all of the work of extracting that game state from simulation and pushing it all the way into the GPU, getting it on screen. fibers really are acting as a convenience for us here. It's not like they're really buying us anything apart from having jobs, because the underlying representation is just a sequence of jobs. But what it does allow us to do is communicate with people. When you look at a big job graph and you want to know and you want to talk to other people about it, if you're not on the same page, then it's really difficult to talk about, oh, this specific job over here, we need to work about this. And getting somebody ramped up to understand that is a lot easier if you basically say, hey, in the render fiber, when we're kicking off the work to extract things out of the frame, people can catch that very quickly. It gives us common ground, basically, to talk about. It also gives you an expectation of how the data is going to be used, because you know what data is associated with it. So there's that general feel of this data is owned by this fiber versus I'm never going to touch the network data inside the rendering fiber. And then the other big key thing that it gave us is, because all of our big systems are fibers, the cross-system dependencies can be documented in one location in our code. I don't know if you've ever had to work in a code base where the dependencies between the systems are spread through the hundreds of CPP files that you've got, but it's a big pain to try to figure out what's going on, especially after the fact. So being able to have that in a single function as 20 to 30 lines is a great way to be able to look and see where that's all going. Time control is the only real thread that we have in our system. It's responsible for kicking off all the iterations of the fibers. It's queued off of vsync for the different platforms. We had tried to do this as a job to keep the entire system as a job, but it basically added a bunch of overhead into our job manager. It was the only job that was trying to execute with accurate timing. And so cutting that out just cut out a lot of overhead in our job system. It's also responsible for serializing all the fibers, which basically just means draining the current iterations. You wait for them all to complete. You're going to do this if you need to run something in a single-threaded type context. So for us, that basically means, hey, we're changing destinations. You're going to Mars. You're going to Venus. We basically need to do a few things where the rest of the game can't run at that time. We'll also use it for system events like suspend resume, or some of our debugging events where we're doing patching and developer mode patching. We don't really care if it works multi-threaded. We just want to have it work. So how did we map this to the hardware? Well, first off, this is a picture of one of our job graphs. This is from Cosmodrome on Xbox One. It's pretty much an average frame. It gets a lot more complicated. I grabbed this frame from Natasha's talk, and it's basically a lot of rendering and a little bit of simulation here. We've got over 100 types of jobs. Basically, hard to really see what's going on unless you can zoom in and move around, which again comes back to the fibers being easier to describe what's going on. So for us, we wanted to keep all of the platforms as similar as we could, and that goes in with our hardware utilization as well. Basically, most of the principles apply to all of the platforms. We usually have one job thread per core. And the simulation fiber, we want to keep that latency really low. We're particular about our input latency, so we need to make sure that we get our simulation work done as fast as possible with as little interrupts as we possibly can. So we're going to try to put this on a high priority job thread across the platforms. So we also have async job threads. A lot of the platforms have tasks that we don't really have control over. They go to sleep. You want to query for your network friends list. Hey, that might take 20 seconds. You're sending an HTTP request to log into a server, or you're loading data off of disk. And so these ones run in our async job threads, which are allowed to run across the serialization events. They can go to sleep. They can take locks. It's basically just calling OS level stuff. And then, of course, we try to keep that data self-contained so that if it does need to get serialized, we don't want to wait for those 20-second jobs. So I'll start with PS3. Basically, this is a layout of what we've done for the hardware threads. There's no affinity on PS3, so it's not like we could say, hey, this job thread only runs on PPU 0. So we kind of cheated a little bit, and we just cranked up the priority as high as we possibly could. And that helps minimize a lot of the preemption that we're seeing on it. And then that job thread is only allowed to run the simulation jobs most of the time. The other PPU thread is another job thread. But that job thread has the lowest priority that we could put in the system. And we basically crammed all the other threads, the middleware and the async jobs in between there so that they can take up time when they need to. And then across all of the SPUs, we use the 6 SPUs. They're just running job threads to consume those jobs. So here's a capture from Tuner. This is job thread 0. You can see here that the preemption, there's not a lot of preemption events. There's still some, but it gets a pretty good utilization. And that allows us to keep that high priority set of simulation jobs going, which essentially are these jobs here. So it's these red jobs that have been marked off here are all the simulation work that's either simulation fiber work or jobs kicked off from simulation. And so they're all running during this time frame up to here. And then this red line that goes down marks the end where the simulation is completed for that frame. And so we've now opened it up so that other jobs or other work can run on this hardware thread. And so you can see a rendering job sneaked in here as this red job here. On the other job thread, you can see up top here, this job thread is preempted a lot, totally reflecting what I said earlier, where we put everything else in between. The SPUs are fairly well utilized. We get about 50 to 70% utilization, which I think is actually pretty good for our first shipped PS3 title. And we're a little bit behind, given that other people are on their like 7th or 8th PS3 title. But this one's our first one, and I think we've done a pretty solid job on moving work to the SPUs. We've got about 20 different job types that cover most of the code base. I mean, we've got audio, AI, animation, physics, networking all running on the SPUs, and of course we have graphics going there too. SP8 lighting, other aspects of the graphics. I think the entire graphics pipeline is running on the SPU for the most part. Moving on to 360. So you've got your 3 cores with the 2 hardware threads each. The interesting one is the first core. So this one's not being preempted by ZAM. You don't have that 1 millisecond time that's getting in. So we're putting all of our simulation jobs there. And then we've gone one step further, and hardware thread 1 is idle for most of the time, and that allows the contended hardware elements not to be used by hardware thread 1, enabling a little bit of a speed up on some of the code for hardware thread 0. That allows our simulation to finish just a little bit earlier. Hardware threads 2 and 3 are just regular job threads. All our middleware is crammed onto hardware thread 4 with the ZAM update. And then hardware thread 5 is also a job thread and some asynchronous jobs. These threads don't move around because 360 has affinity that we can lock the threads to the hardware threads. So this is a capture from Rad Game Tools Telemetry, one of their older versions. This is a frame from the 360. It's a little bit harder to see what's going on here because we're not zooming in and whatnot. But this red circled section here, this is all the simulation work. Everything past that is moving on to different jobs where we finish the sim frame for 360. You can see in these circled spots here, this is the spots where we've left the second CPU idle so that we can actually get the better performance on the first CPU. And then this red line over here, again, marking where simulation is complete for that frame, and we've opened it up for the rest of the jobs to be able to execute on that thread. So on PS4 and Xbox One, there's the 2 clusters. Basically use cluster 1, so core 0 through 3, to run all of our jobs. Again, core 0, it's our simulation jobs. That's the only jobs it's going to be running. We want to keep those as high priority as possible, just like on all the other platforms. We're able to set the affinity so we don't have to worry about the threads moving around. And on the second cluster, we basically run all of our middleware and any of our async jobs. So here's, again, a telemetry capture. This is from Xbox One. The PS4 is fairly similar, although it's a little bit more idle than the Xbox One is. You can see again at the top here, these jobs are a simulation workload. On next gen, we are able to complete the frame relatively quickly. And then we've got our rendering that starts in after that. And we actually finish the rendering almost within 33 milliseconds. We almost don't need to pipeline for next gen. So I'm going to move on a little bit. You're going to see how we prove that our code base is thread safe. Because all of that job graph is fairly complicated. We basically want to be able to say, hey, this is totally safe, right? So the big requirements here to be able to say that is we need to be able to get actionable bugs when we're getting it. We can't have those bugs like I talked about earlier where it's like, here's a video that says that the rocket looks the same. We need to be able to know when that's actually happening, how often it's happening, and then why it's actually happening. And then we need the tools to actually be able to debug it. And really, we need to enforce our data patterns. So I bring up this picture that we had at the beginning. And you see the physics going where it's conflicting with the raycasts again. We want to be able to robustly detect this bug. And how do we do that? We need to do that because we have 50 client engineers all banging on the code. So we came up with our execution environment. This is our solution to this, the thing that let us ship across all of our platforms. And it's really a system to validate resources and to make sure that the patterns used with those resources are actually going to be thread safe. Our goal is really to satisfy those multi-threaded requirements that I just said. So it's going to be identifying unsafe patterns, but it's going to be doing it during development. You're not going to be waiting to find out later after you've checked in. It's not going to be 3 months later. It's going to be before you've actually submitted it and unleashed it upon the rest of the people who are developing in that code. It's also going to find the potential issues without you actually having to hit them. So we want to make sure that if it's possible to have this race condition, we found it, not only when the race condition occurs. And it's going to detect any of the patterns that lead to the weirdness that you're going to see that's hard to debug. Like those things where, hey, if this job runs in a different order from this job, you get a different result. But you can't tell and you can't really debug that because how do you control which jobs run in the different order without having putting dependencies between them? And then if you did put dependencies between them, then you've already fixed the problem. It'll also catch any of the data race conditions or any of the other crazy bugs that you're trying to find that are all based off of code running at the same time, banging on the same data. But I do want to stress that this is verification only. We don't ship with this. It's totally compiled out inside of our release builds. We're not doing any synchronization as a result of what we find. It's strictly, we're going to assert when we've detected that you're able to do some sort of access that's not good. So I'll talk a little bit of terminology. We have a resource. It's just really a theoretical concept. It's nothing specific. It's not a data structure, but it's anything that you would want to have protected. So, anything from our Havoc world to actor data, maybe your input controller, anything that would be used in a multi-threaded fashion. We have policies, and these policies describe what you can do with a resource. We want to be able to say, hey, this job is allowed to pull the controller. This job is allowed to read physics. Those policies are associated with a job, and it's really just explicit markup that you have to add into the code. And then we have to provide resource access checks for everything. Any resource that you want to have protected needs to be able to look up into that policy to see if it has permission to do that work. And so you need to be able to put in all of the hooks. And then, of course, you have to actually have a lot of code coverage to be able to go through all of those if statements and all the different pathways through your code to make sure that your policies are actually properly protecting that data. And then for our access checks, we're going to assert, as I mentioned before, when you don't have access. And that's going to be a clear assert that basically says, hey, no, you can't read game time from here. You're the renderer thread. You have to get it some other way. The policies can overlap. This is when you have resource usage that conflicts. So maybe you're, like the example before, raycasting, but you're also updating the Havoc world at the same time. That's not a good thing. These also trigger an assert, and it's going to be a clear assert that says, hey, your raycast job is trying to read the physics world, but you're also writing to the physics world from your Havoc update job. These are really to detect potential race conditions. You didn't necessarily hit the race condition. Maybe it was totally safe to read the Havoc world and do those raycasts when you were updating it, because the jobs that, or the parts in the physics world that you were updating weren't the parts that the raycast was actually looking at. But it could happen in the future. And then we're going to check this against all of the jobs in the job graph. We basically integrated the execution environment to be able to know the dependencies between those jobs so that we can actually tell which jobs are capable of running at the same time. And this basically makes us provably safe. So as long as you have instrumented all of your data access, exercised all the pathways through your code, and you're only using jobs, then it's perfectly proven. I realize that that's, a hard, tall order to ask for, but it's not as bad as you think. So I'm going to talk a little bit about how we actually implemented that, got it into our engine. And to start off, writing code. This is how we basically write all of our code. And you're going to start off doing your planning. You're going to plan what data access you're going to have. You're going to add access checks for all of the resources that you're going to need. And then you're going to add policies to all the new code that you're writing that basically expresses what you're going to do and how you're going to access that data. You're going to run through all the code pathways. And then you're going to resolve any of the overlaps that it's found. So I'm going to talk about these pieces in a little more detail. The first part, catching every resource. You can't really just say, hey, everybody mark up every single pointer dereference that you're going to do. That's kind of crazy talk. Nobody's going to do it unless you're forced to actually do it. And if you don't have compiler support to force those people, you pretty much have to put a wrapper around every piece of data inside your engine. But thankfully for us, from previous titles, we actually use handles for all of our data access. So we had a single point that we were able to put those access checks in and be able to verify that we had the safe spot. Handles have been great for us. It's used for every piece of data in our engine. We just found cache pointers are very often causing bugs. You can't tell that this thing has been deleted frames ago, but with handles we're able to actually see that. We have salt in the handle that basically says this has been deleted. It's not the same one as when you took the handle from before it. So we can have a nice easy assert that says, hey, this simulation object that you dereferenced is no longer up to date. So the data types that we have, global data, this is your standard structure that you would normally use. We've wrapped it with a handle. The only piece that's actually really global in this case is the pointer into the data structure that we've backed in the fiber memory area. And so that's that area that I said, the network state at the beginning, where we had that associated with the fibers. And that helps group the memory that's used a little bit more cache coherent as well. And this accounts for about 10% of all of the data in our game state. We also have arrays. These are our typical C-style array. We call them datum arrays. The only difference between this is it's got an element of sparsity to it. You can have different elements that are not allocated. So in this example, datums 3 and 4, the gray ones, are not allocated, but datum 5 is. So there are holes in there. These are also accessed with handles, and this accounts for the bulk of our game state, about 80%. Datum array with heap is our solution for variable size data. The big usage case of this is all of our content memory. All of the resources that you're going to see, of course, are different sizes throughout the game. And it's really just a datum array that indirects into a heap. So with those data resources, these are the access checks that we've actually chosen to provide. There's your basic protection, which is just read and write, which is exactly what you would expect. We provide array protection for the datum arrays and the datum array with heap. It's array modify, array iterate, which I'll talk about shortly. And then there's some advanced protection, producer, consumer, and whitelisting that we'll talk about after that. So array modify is really protecting the life cycle of data. It's about whether or not that allocated status can be changed or written to. And so in this example, it's, hey, datum 0 going from unallocated to allocated. And it covers the destruction side as well, going the other way. Array iterate is the read side of this allocated status. It's anything that you can do to discover data. So it's meant for the typical loop that you're going to have where you're walking over all of your data, doing something for every single element. But it also covers being able to count or query whether or not a piece of data inside that datum array is available for usage. The producer consumer is our solution to allow things to create and remove elements while other jobs are capable of reading or writing from that data. And so this is the case where you're loading all of your assets into the game. You need to still be able to read every other asset when you're loading new ones or creating new ones. In this example, the object update is running, the actor update, rendering objects, they're all going to read into the content. And so they still need to be able to read that content when your assets are loading. Or another example, you've got AI. Maybe you have a job that's spawning new AI while you've got other jobs in parallel that are updating the existing AI. You're going to want to be able to do that without having to serialize those operations. And the producer consumer allows us to represent that in the execution environment. Whitelisting is our solution for data parallel jobs. It's about breaking up one datum array and allowing different access for each element within it. So you can see here we have 3 actor update jobs that are taking 2 actors from the datum array above it. It doesn't need to have the exact same thing. It's not saying, hey, these ones all have write access. It could be that the actor 2 and actor 3 are only read access in this case, whereas the actor 0, actor 1 is write access. So you take all of these permissions. Here's an example of what a policy looks like in our engine. I apologize for showing code, but gets the point across. Basically, we have a policy builder. You add access to it with writes or reads for the different pieces of data, and then you associate it at the end with one of your jobs. So you've taken all of that, and we get to the point where we have to exercise all of our code. So this is a picture of our stress lab, or one of the parts inside of our stress lab. We do a lot of automation in our building. We have 150 machines that are dedicated just to doing stress for PC side of things. We've got 200 machines that are dedicated to doing builds across the studio, and then another 200 machines that are doing content builds for us. In addition to that, we've got 600 different consoles inside there that's running test cases on it as well. And so every time you check in code, we actually run a stress run for your build. And then we have overnight stress runs, or sometimes longer, that run a more exhaustive test suite on it. And this is to cover all of those cases. And those stress things aren't just, hey, run this same test over and over again. Some of them are monkey scripts where we basically just provide random input to controllers that you are capable of exercising code paths that you wouldn't normally use. In our last month, I think we've done about 12,000 hours of stress run, and then 2,000 runs of just check-ins where we've done stress against those. So you found the overlaps. You need to resolve them in some way. And there's really only 4 ways to resolve these issues, and they're the standard ones that you're used to. You can add a dependency between the jobs. If the 2 jobs are dependent on each other, then they're not going to run at the same time. The data's not going to be overlapping. You can double buffer or cache your data. So maybe you want to read at the same time. Maybe you duplicate that data in a pre-job and pass that into the jobs that read it while you've got the other jobs updating it. You can do the opposite. You can queue write messages. So you know you want to update the actors. So you build up a big list of operations to proceed, and you do that at a point where the actors aren't being used elsewise. You're basically making it a single-threaded part in the future of that frame. Or the worst-case scenario, you have to restructure your algorithm. You just fundamentally can't do it. And that's the hard part. And those are the parts that you want to find early on where it's just not going to work. I'm going to talk a little bit about the overlap algorithm. It's a fairly simple algorithm, but it's not really obvious until you've really thought about it. And so in our case, we're going to take this example frame where we've got our AI kickoff and finish with our actor update jobs in between. We've got another job that's not part of this dependency chain, the network send, and then after the AI is finished updating, we're going to update the rest of the objects in the frame. So the question here is, which jobs can overlap with this actor update job here at the top? And so step one, we're going to traverse down the dependency tree. We're going to mark all of the children of this job. So all of the jobs that can't run until this job is completed, those ones clearly can't overlap. So in this case, AI finish is dependent on the actor update job. And then afterwards, the object update is dependent on the AI finish. Step two, we're going to go the opposite way in the dependency graph. We're going to make sure that all of our parents, so the jobs that need to complete before we can run, have been marked off as non-overlapping as well. In that case, this is just the AI kickoff. For the third step, we're going to union all of the jobs that we haven't marked, and we're going to take the policy from each of those jobs and build one big, giant global policy that encompasses all of the access that those jobs can have. In that case, this is the two actor update jobs and the network send job that we've got here. For step four, we check that policy to see if that policy has any conflicts with our current actor update. And so for this example, we're going to say, hey, maybe the actor update job just gave full write access to all of the actors instead of doing a whitelist. So in that case, there will be a conflict. And we take the conflict, and we're going to walk all of the jobs that we just finished unioning, the policies for that, to check those individually so that we can get finer detail information about what's actually overlapping. So we walk it. We see that the actor update, as I mentioned before, it's conflicting with the first actor update. So we take note of that. Likewise, with the other actor update, it's also conflicting. But the network send job isn't. It's not using any data that the actor update job is, so we can mark that as not conflicting. And so for the final step here, we basically just report the errors and assert out. So you're going to get those nice clear errors that I was mentioning before that says, hey, the actor update is busy writing to the actors while the other actor update is also busy writing to the actors. So you know what to go and look for from the get-go. And you didn't spend time trying to figure out later why your actors were being clobbered by other jobs. I'm going to talk about the lessons that we learned from actually implementing this. Retrofitting this system into an existing code base takes a long time. We should not account for how much time it was going to take to mark up our code base. It was actually longer to write markup for jobs that already existed and the multi-threading that was already there than new jobs. You just don't know all of the nuances of what's going on in the code. You haven't looked at it for who knows when. You may not have even been the person who wrote the code in the first place. So you end up with this tail of bugs that you get where you're getting those asserts that say you don't have permission to read this piece of data because you didn't realize that it reads this piece of data on the off chance that your player is looking up while jumping. And then, it was just this unending feel where we kept going at it and kept going at it. I'm pretty sure it took us multiple months with multiple people to do it. So we learned we really needed a relief valve. As soon as we put this stuff in, we were getting asserts all over the place. We had issues in our code base that we've been skating by for a while now. And then that workload just explodes on all the other people's teams because you're saying, hey, maybe there's an issue in rendering. Maybe there's an issue in the AI update or animation. And you're basically saying, hey, you now need to stop what you're doing and fix this multi-threaded bug. But you can't really do that, and you can't really do that all at once across your entire studio. So you need to have a way to ignore the issues or filter out the issues so that you can basically add a bug, forget about it, let the game run, and then at least know that it's going to get fixed when you triage your bugs later. We also had this great experience where we thought we were smart. We're going to roll this out in phases. We're going to start off by adding all of our resource protection to every piece of data that we've got. Then we're going to enable resource checks first. We want to enable overlaps. We can deal with that later. It'll be our second phase of rolling it out. But if you don't educate your team on what's going to happen, then your team goes ahead and just gives full permission to every single job. And then you turn on overlaps later thinking it's going to be an easy time, and every single job in your system overlaps with every other job, even though the data is not being used. And so that comes back to trying to keep your policies tight with what you're actually doing, because the issue may not be a real issue. It may just be that you've oversubscribed that job to different data that it can use, even if it's not using that data. And there's a balance there. You can't protect all of your resources. I mean, I suppose you could if you really wanted to spend all of the time, but it's hard to represent all of the safe operations that you can do. There's a lot of things that's really easy. You can be clever and try to pack data into different fields. You can try to do substructure allocations and think that it's safe for two jobs to be able to write to a different field inside of a structure, when really it's not, because it's going to clobber it from some weird read from the compiler because you didn't do it on an atomic level for the chip. And so this really helped discourage that cleverness, but you really do need to figure out what level you're willing to go to actually protect. And we did that by restricting what programmers could actually do in some cases, just to make it simpler. Validation is not fast. It gets slower and slower every time you add another job. Those overlap checks are essentially n squared. And so we really just do the full validation steps inside automation. When you're checking in, you're doing a validation, but it's not the full exhaustive validation that you're getting from our automated farms. But we also found that it improved communication within our studio. You think that you've planned out your data well, and everything seems fine, but then you go and you implement it, and it just doesn't work. Somebody's using that data in a way that you didn't know. The person who originally designed it didn't know that people were using the data that way. And then, of course, the engineer who originally wrote the code and thought that the data was only going to be used in one way now finally has a way to assert that that's going to happen. You don't have to wait for some bug that you get 6 months down the road that says, hey, Joe Blow decided to use this data, and I don't want him to use it right now because I'm busy writing to it. So really, engineers ended up talking to other engineers. You ran into an assert from this, you got an overlap, and you wanted to find the right solution. So you ended up working with the people who architected the original system. And that was fantastic, especially for new hires or contractors, because those people have just come into your code base and they don't really know anything. They're trying to get in and they're trying to do the best that they can. And sometimes that just turns into, I'm just going to make it work. And this system was a good way of saying, you think it's working, but it's not, and we're not going to let you keep that code checked in. It's actually faster than fixing it later. It seems like the upfront time is huge. It feels like you're spending more time overall, but you're really not. You're actually doing the fixes for this right away, right when you're doing the code in the first place. You actually know what's going on. It's not the 3 months later I've come back, what the hell was I thinking? I don't know what I did in this function, and I'm never going to remember it without reading through the whole thing. But you haven't even checked the code in at this point, and it's telling you that it doesn't run because it has data conflicts over here or data conflicts over there. But it also has the advantage that when you walk away from the system, you can actually walk away from the system. The bug tail ends. You get all of the issues up front. It's not going to last for the next 2 years of your life when you try to figure out why the renderer can't work with the particle system. The other interesting piece that we had is reorganizing our frame was actually really easy. We had multiple occasions where people just decided, hey, I want to be able to get more use of the CPU during this area, so let's just figure out what runs over here. And the easiest way to do that now is by trial and error. You can try 20 different places where this piece of code can run, and the system will just tell you, no, you can't run there, you can't run here. Or it'll let you through for the one place that's there, and you know that you can just leave it there without having to think about it. And so you're not in those meetings trying to discuss, maybe it'll work here, let's try this out. And then you've got those 3 or 4 days when you have tests banging on it to hope that you find some crash. But you can actually do something crazy like change it just before beta. So to wrap things up, in conclusion, we shipped 4 platforms. We didn't have any threading issues that we were aware of. We had fewer threading bugs overall coming out of test than we had on our previous titles. And those previous titles were only on 1 platform. So four platforms with fewer bugs than 1 platform was pretty awesome. We're pretty confident that we wouldn't have been able to ship without the execution environment. But the execution environment can't actually protect everything in the system. Was it worth it? Absolutely. We had to do it. No questions. We have some other Bungie talks. Natasha's talk on the rendering architecture is next at 5:30, room 3005. Butcher has a talk tomorrow on the core architecture of Destiny and the learnings that we had from it, which was fairly interesting. And Justin Truman has a talk on how we did our mission architecture for multiplayer. We're hiring. Come work on the platform team. Work in this environment. It's awesome. Any questions?
Hey, that was really cool. What language features do you use to declare the dependencies of jobs when you write jobs?
So it was just in C++. So a dependency from one job, we had a command, A depends on B, and you pass in the handle for the A job and the B job.
And I'm assuming you do this like via some sort of dynamic analysis that tries to just...
Yes, at runtime, we check the job graph. That was the overlap algorithm. And then every time the handle dereferences, it's checking whether or not you have the policy permission.
Have you explored doing like static analysis or something instead?
There's a certain element that you can do in static analysis, but you can't cover everything, so you end up needing the dynamic analysis as well. So at the end of the day, you can cover 80% one way, but you really do need that final 20%. So there's an area that you can explore so you can catch it at compile time, but you catch it pretty fast at runtime.
Thank you.
Did threading your client in this way present any challenges trying to share gameplay code between the client and the server?
It's a good question. We certainly had issues for pretty much everything that we did, right? Any threading had consequences from one place or another. As for the server side, most of that stuff's already serialized via the networking code. You're sending packets to it. It's a big buffer. So I don't know of anything that comes to my mind as this was a real big issue for the server-client architecture doing it this way.
Cool.
Hello, this side. And I have 2 questions. First, how to define a complete code path?
Sorry, how do you define
a complete code path to test?
That's the same problem that you have with any case where you're trying to get full coverage over your code base. For us, most of that was done via explicit testing where we knew, hey, if you do this, this covers all of this. Getting rid of branches that seem unnecessary if you don't need them. Our stress farm, again, with the monkeys that I mentioned earlier, where it's just a big stream of random input that helps get that coverage. I can't guarantee that we hit 100%, but...
How long machine hours will you test?
How long in hours was the unit test? It depends on the level of testing that you're doing, but like a check-in job is probably about 1 to 2 hours. the full BVT test suite is easily, 20 hours, if not more.
Okay, and another question. We are putting our engine to the multi-thread architecture, and we face the same problem that there are a lot of older systems that are doing multi-threading in older ways. And we found that it's better to port the entire system to the new architecture in one time. So we open up a branch, and when we finish doing this and porting back, we find a lot of new bugs flies out. So I want to know, how do you change your old systems to this new architecture, step by step, or any other suggestions?
So if I get the question right, as you're adding this to an existing architecture, how do you catch all of the bugs without...
older systems, you just mentioned that.
The older systems,
Yeah.
yeah. So, I mean, for us, it was mark up all the data and make sure that the access checks are going. As you find that, you're going to see overlaps. We had a system to filter out those overlaps, so we would know about it. We'd create a bug in our database and basically just say, don't report this overlap to any user who's doing it until the person who's gone responsible for that bug actually fixes it. So that's allowed us to basically turn it on for the old systems without exploding it everywhere.
Okay, so you have two systems running simultaneously at certain points, the older system and the new system?
So, I mean, you have a toggle in some way to switch between those systems, right? Like, you're just going to hit that as you toggle between the systems.
Okay, thank you.
Thank you.
Hi, so if you had all these really nice systems for determining when data contention happened, why did you build this like gigantic validation test system?
Well, the validation test system is the thing that's telling us about data contention.
Well, doesn't it just tell you up front whether or not you have contention?
It does, but it's the only piece of our system that is telling us about that contention. It's not, so the handles would tell you whether or not they've been deleted. The handles don't tell you whether or not somebody else is accessing it. This is the piece that takes that information from the handles and then cross-references what every other piece of data is doing.
So it's doing that like after the fact?
It's doing, part of it is up front. So every time that you access the data, it's checking dynamically right there and then for whether or not you have permission. And then the overlap checking is after the fact. We keep about 3 frames queued up so that you can see which jobs within there could be running long. And that piece is just done whenever the jobs are being added to the graph. It'll go across all of the other jobs that are previously there.
Thanks.
Hi. So also related to this question that was just asked. So once you have handles, once you have policies that specify what data you can access and how, and handles that let you track the data as you access it, how do you deal with, like normally every engine is going to have a certain amount of third-party software that is not going to have handles in the code. So like once you have some components that just use row pointers.
Yes, there's lots of middleware that just use raw pointers. We've done things where we've embedded, like our raw pointers for the user data is just pointing into a handle. We've had other parts where inside that actual callback that you might get, you actually are explicitly calling into the execution environment saying, hey, check this access. There's a few spots where, I've simplified some of the details where it's not just in the handle access. There are those places where that thread that's running in Havoc that's calling your code is not actually a job. And so the system does handle that via other mechanisms.
Okay, so it's like on a case-by-case basis, basically.
Pretty much.
Okay, cool, thanks.
I had a question. What types of data did you end up double buffering?
What types of data did we end up double buffering? There's a lot of stuff that we ended up doing. There was the weirder esoteric ones, like a bunch of simulation state for timing information for networking because of the time frame when networking ran. It ran where simulation was going, but it could have lagged over the frame, so it couldn't actually directly access that. That was most of the time that we were doing the caching. If you go and use see Natasha's talk, you'll find a big section that we double buffered from the game state for rendering. Not the entire game state, but portions that went out, and that probably encompasses the bulk of what's there.
Yeah, it seems like if you're updating game entities all in parallel, don't you need to double buffer their states so that you
So in
get a
that case, we
consistent
actually, the way that we update those entities, we have families, object families. So if an object is likely to touch another object, it's going to be updated in the same job.
Oh, okay.
And
Thanks.
then furthermore, if it has to touch a job or an object that's outside of that job, it'll just queue a message. And we have a final message drain at the end that can process interactions like that so that we don't have those problems.
Okay.
Okay. So do you only detect bad accesses on like dynamic tests, or do you do it on like commit as well?
So we don't need to do it on commit because the scope of a policy is within the entire job. So in order to actually commit, you need to dereference the handle, and in order to read, you have to dereference the handle. We do differentiate those with different functions so that we can choose whether or not it's a read or a write, but that's just done at the time that you're dereferencing it, and it's safe because later in the scope, you still have the same EE policy.
So by commit, I meant like a git commit.
Oh, I see. So yes, for our submission process runs through the automation, and that's our gauntlet process. And that's done where you'll get kicked back. You won't be able to submit if your code doesn't run.
So this is a pretty inherently complex system, and you acknowledge that. Has this, what do you guys do for code? Like, how do you code review code, like Fabricator, GitHub, or so on? And has it added a lot of overhead or time on your people on your team having to review a lot of code for people that aren't as familiar with the system as you guys are?
So, I mean, depending on the time frame where we're in within the production cycle, the amount of code review that we do is different. The closer we are to a release point, we have more code reviews going on. But for the added amount of code review for the extra policy, it's not usually too much. There was definitely a lot right up front when we were rolling out the system, and it did add a lot of work for a lot of teams. But in the current state, it's basically, hey, did you run this in the test build? Did you actually check that it's working? They say yes. You generally look through their policy to make sure that it looks like it's doing the right thing. You know, it's not a huge amount of time.
And this might be a naive question, but if all of your jobs declaratively declare what their data dependencies are, why do you need to dynamically run them?
So you don't need to dynamically run them in order for that portion because you've got that piece already running. That piece is actually statically checked. It just happens to be that some of the jobs are run in different orders on different frames, so we do check that at the frame level. But for the pieces, like the question earlier, where it's like, hey, what do you do when middleware is calling into this code? That actually needs a dynamic check going on it because you don't know the dependencies between that piece with the rest of your game frame.
Cool.
Cool.
Hi, I was wondering if, in addition to your sort of built-in system, that you tried using third-party thread checking software like Thread Sanitizer with Clang or Intel Inspector.
Sorry, can you repeat the question a little bit louder?
Right, sorry. I was wondering if you tried using third-party thread checking software in addition to what you've been doing, so Clang's Thread Sanitizer or Intel's Inspector, which will do runtime checks for...
So we do have some static analysis that we run offline.
Okay.
We didn't investigate a huge amount of the other pieces. A lot of those times you get a big bucket of work items that, you know, filtering the signal through the noise is really hard in those systems.
Yep, okay, thank you.
Thanks everybody for coming. Please fill out your form survey thing.